All right. The cosmic microwave background is a microwave radiation that fills all space in the observable universe. With a standard optical telescope, the background space between stars and galaxies is almost completely dark. However, a sufficiently sensitive radio telescope detects a faint background glow that is almost uniform and it is not associated with any star, galaxy, or other object. This glow is strongest in the microwave region of the electromagnetic spectrum. The accidental discovery of the CMB in 1965 by American radio astronomers Arno Penzias and Robert Wilson was the culmination of works initiated in the 1940s. The CMB is a landmark evidence of the Big Bang Theory for the origin of the universe. In the Big Bang, cosmological models during the earliest periods, the universe was filled with an opaque fog of dense hot plasma of subatomic particles. Excuse me. As the universe expanded, this plasma cooled to the point where protons and electrons combined to form neutral atoms of mostly hydrogen. Unlike the plasma, these atoms could not scatter thermal radiation by Thomson scattering. And so, the universe became transparent. Known as the recombination epoch, this decoupling event released photons to travel freely through space. However, the photons have grown less energetic due to the cosmological redshift associated with the expansion of the universe. The surface of last scattering refers to a shell at the right distance in space, so photons are now received, were originally emitted at the time of decoupling. The CMB is not completely smooth and uniform, showing a faint anisotropy that can be mapped by sensitive detectors. Ground in space experiments such as COBE, WMAP, and Planck have been used to measure these temperatures and inhomogeneities. The anisotropy structures determined by various interactions of matter and photons up to the point of decoupling, which result in a characteristic lumpy pattern that varies with angular scale. The distribution of the anisotropy across the sky has frequency components that can be represented by a power spectrum, displaying a sequence of peaks and valleys. The peak and valleys of the spectrum hold important information about the physical properties of the early universe. The first peak determines the overall curvature of the universe, while the second and third detail the density of the normal or so-called dark matter, respectively. Extracting fine details from the CMB can be challenging since the emission has undergone modification by foreground features such as galaxy clusters. Here we have the picture. You can see maybe the lumping, the anisotropy. This is a 9-year Wilkinson microwave anisotropy probe. Heat map of the temperature fluctuations in the cosmic microwave background. All right, hope you guys enjoyed.